Hi-oh, here we are, diffraction and interference. The bubbles you see on the screen are a great example of interference. But before we get to interference, let's talk about diffraction. Diffraction is simply the bending of waves as they go through openings. If you remember, refraction was also the bending of waves, but the waves were going into a different medium. Here, it's staying in the same medium. You can see in the examples, for example, the one in the upper left-hand corner, how waves going through this opening bend. You can see how they've curved around. Same thing, here's an object sitting in the water, and the waves are bending around that object. Something more familiar you may not have realized is that there are openings in the clouds that the sun shines through, and the light rays are bending. They're changing direction. It turns out that the size of the opening compared to the wavelength makes a big difference on how much that light will bend. A very simple way to know and understand exactly how much it will bend is if you can easily go through the opening, you, meaning the wavelength, you're not going to bend much. So imagine trying to walk through a door, an opening the size of a house. You can get through it without any problem. But if that opening is smaller than you have to twist and turn, in which case you're going to change your direction trying to get through. Waves are very similar. Small wavelengths go through openings much easier than bigger wavelengths. As the bigger wavelength compared to the opening tries to go through, it will be forced to bend. Even if we have a smaller wavelength, if we change the size of the opening so that wavelength is much smaller than the opening, it will bend. An application of diffraction would be an electron microscope. The waves used in an electron microscope are very, very small. So larger objects cause those waves to bend and create shadows. And so you get a sense of depth perception. Down below, you can see examples where scientists have manipulated atoms to spell out words. For example, they took atoms here and they spelled out the letters IBM. Not to be outdone, USC, University of South Carolina, did the same. Diffraction gratings use this idea because the openings are very, very small. You can see an electron microscope view of the little tiny scratches in the film. As the light goes through those openings, it bends. It turns out longer wavelengths tend to diffract more. And because of that, the light gets scattered and you get the entire rainbow. Before all this diffraction grating stuff was made, before diffraction was truly understood, we had some experiments trying to understand the nature of light. A gentleman by the name of Thomas Young, who was a child prodigy, did a very famous experiment. He had shown light through a couple of different slits, and of course light through the one slit would interfere with the light through the other slit, and he tried to deduce exactly how light behaved. Was it a particle or was it a wave? Well, upon the interference, he realized that if we got banding, that it would be the wave theory, because we would have constructive interference, destructive, constructive. If it was a particle theory, there would be a continual spectrum going from very bright, getting less and less bright as you went. What he observed was that was consistent with the wave theory, where we had constructive interference and destructive interference. You can break this down into what he saw. Two crusts interfere, and they're in phase as we know, and that's constructive. We would see bright. If we had a crust and trough interfering, they'd be out of phase, or destructive, dark, and so forth down the line. And that's exactly what he saw. So he concluded light behaved as a wave. You can try this yourself by taking your fingers, put them very close together, and have light pass through them, and you should see light-dark bands between your fingers as the light interferes with itself, going around each edge of your finger. Thin film interference, exactly as it sounds, it's the interference of wavelengths on a very thin film. Basically, we get constructive or destructive interference because the thickness of the film is some interval of the wavelength. So if we use 1 meter as our example, the wave is 1 meter long, and the film were to be 1 meter thick, it would reflect upon itself and actually reinforce itself, and you would get a brighter color. Let's look at this in a little more detail, only showing cancellation. Let's say we have a beam of blue light coming in. It hits the surface of a thin film. Some of that light reflects off the surface. So here's this coming in. And of course we have that blue light reflecting off the bottom part of the surface. And notice the thickness of this film is half a wavelength. We only have a crest, and the other half would be the trough. Notice what happens. That crest, that as it's reflected off the top surface, interferes with the trough that's reflected off the bottom surface, and blue light gets canceled. Well, if you get blue light canceled, what are you left with? The primary colors are red, blue, and green. We cancel the blue, we're left with red and green, which gives us, you guessed it, yellow. So, what happens when we shine white light? Red's canceled. Keep that in mind, right? Red, blue, green. We cancel red, we're left with blue-green light or cyan. Blue is canceled, we're left with red and green light, which of course is yellow. And if green is canceled, you're left with red and blue light, which is magenta. Of this light, realize light given off by most sources are very jumbled. We get all the wavelengths, all the frequencies. It looks like a bunch of spaghetti on a plate. What if we were to get rid of all of the other colors and just have one color, or in other words, make it monochromatic? Well, it might look like the picture shown here in the middle. Now, what if we could take it one step further? What if we could cause all the crests to line up and all the troughs to line up? We would say that this is coherent light. All those crests would, of course, interfere with each other. All the troughs would interfere with each other constructively, and we would get a very bright spot. And that's what a laser is, which is, of course, the light amplification by stimulated emission of radiation, laser.